All right, our last thought on this particular section about musical instruments is about a different type of tube. Some musical instruments are closed at one end. So if we look, for example, this is a great example of a closed one. This is a water bottle. It's open on the top, so when you actually blow air into it, it's sealed on the bottom but open on the top. And there are woodwind instruments that are exactly like that. Now, let's take a drawing of our waves again. When it hits the wall in the back of the closed tube, doesn't it stop the wave and say, hey, can't do anything here? That's a node. In the very front of the tube, where the tube is open, if we look here, isn't it free to move up and down here? So we've got ourselves an antinode right in the very front. So if we look here, because it's an open area, the wave is able to move freely as it wants, and this is an antinode up in the front. All right, let's take a look at our wave itself. And if we look at a wave, the whole wave goes up, goes back down again, and it looks like this. Start here, and then this is our final spot for our wave. Now, let's take a look at this wave. It starts at the top and goes back to the middle. So we start here and end up back in the center, from here down to here. How much of a wave do we have? Yep, trouble, trouble, trouble. So the length of the tube is related to 1/4 of the wavelength. And then, of course, we can redo this formula. L is going to be equal to V divided by 4F. All right, so if we look here, this is known as the first harmonic, or the fundamental, once again. All right, this is the main note that you would hear from that musical instrument, and it obeys this formula. The bad news is this is not the same thing as a guitar string or an open tube. We've got ourselves a situation where we've got a different denominator, and it's going to be half as large. All right, so you're saying to yourself, well, if the fundamental first harmonic, there's got to be other ones as well. So let's draw those. We've got ourselves the next harmonic right here. Okay, now when I'm drawing this, I'm thinking to myself, I know that I've got an antinode up here, so I'll let things go. I've got to have some movement there. And on the back wall, I know that I have a node. So somewhere in this, we're going to end up with another node. So when I draw it, it goes like this, downward, goes all the way up, and then comes back. Good luck drawing that one. Okay? And once again, I hope you did a better job. Goes up and then back down again. I stretched it out a little bit too much. Not too bad, though. All right, this is called the second harmonic, or the first overtone, once again. All right, and our value here, L is going to be equal to, well, let's check our wave. We start at the top, go to the middle. Start at the top, go to the middle. Check. All the way to the bottom, all the way down to the base. Back up to the middle again, and if we look here, we've got ourselves, see, 1/4, 1/4, another fourth. Oh boy, tricky, tricky. We've got ourselves 3/4 of a wave. If I do this in terms of velocity and the frequency, we end up with 3/4 V divided by F, something along these lines. Now, I would call this the second harmonic, but I lied. All right, let's take a look at the numbers. Up here, there's a 1 here for the first harmonic. Here, we've got ourselves a 3. So 3 is the determining value. This is not the second harmonic. This is the third harmonic. Why? Because we've got the 3 in our formula here, and if we look there, it is that 3/4 that is determining the harmonic. All right, now you say to yourself, well, gee, we went from first harmonic, where's the second harmonic? And the answer is there isn't any. So when we're dealing with closed tubes, a trick question would be, hey, draw a second harmonic for a closed tube. You'd say, Mr. Hessler, no, I'm not going to do that, because I know they go from first all the way to third harmonic. All right, now, knowing this, we've got ourselves a nice little situation, I'd like you to draw the fourth harmonic. I'm not, you can't trick me like that, no way. So I'm saying to myself, first, third, there is no fourth harmonic. All right, so we go to draw this. All right, I want you to fill that back in, please. All right, draw your tube like this. You know that there's a node at this end, antinode here, and that you know that there's going to be two spots on the inside of the tube to draw. So if we draw the fifth harmonic, see if we mess that up. Node here. We're going to end up needing a node and another node, like so. So let's see if we can draw it down here, back up, over there, like that, yeah, and then back to the middle. All right, how much of a wave do we end up with? It's 5/4 of a wave. So we end up with 5/4 of the wavelength, translating that into our V divided by F formula here. And notice that we've got ourselves the fifth harmonic. So in general, we have a new formula of it. All right, and if we get rid of our little wave picture here, the generalized form for an open tube is going to end up being, well, on the denominator part, we've got to keep the 4 down below, V up top, F here, and then N would be the number of the harmonic. Let's see if this works. First harmonic, 1/4. 1/4, yeah. Third harmonic, 3/4, boom, working. Fifth harmonic, 5/4, boom, formula's working great. Now remember, only use this when you're doing a closed tube situation. All right, now, if we go back to our analysis over here once again. All right, let's take a look at our situation. So if we take the generalized version of this formula, L is equal to NV divided by 4F. Let's see how this works out. All right, we know that the number 4 is constant, so I'm not really concerned about that particular number. The harmonic itself, so we'll check within, say, one harmonic. We could pick one, first, third, fifth, whatever we like, and that's just going to stay the same when we're in that particular harmonic. So what's the relationship between the frequency and L? So once again, if we look here, the frequency comes over here, V is constant, and L is in the bottom. All right, so if we look, we've got our frequency is proportional to 1 over the length. So when we say the length of it, let's see if we can change the length of this closed tube. All right, now, in the soda bottle, I've got ourselves a black cherry seltzer. Great for lunch. All right, and I filled it up with water up to this point here, and it's pretty full. So let's put some air into it and see what we get for a frequency. Now, we notice that the frequency is proportional to 1 over L. What I mean by L is the distance that the air column can actually move up and down. So when it hits the water is actually becomes the wall itself. So the water is stopping the movement of that wave. So this has a very, very short length to it. If the length is small, that means the frequency is, you got it, high. Let's try it. All right, now if we take that, boy, that Lenape water is delicious. Arr. Try it again. Now, I've drank some, so now the length of it is actually a little bit longer. Let's try it now. Did you hear the pitch change? Definitely lower. Water bottle's half full now. Try again. And try one more time. And boy, I'm full. All right? I'll pour the rest out. Maybe we can get something out of it. Boy, that's starting to get a little low. All right? And then notice, as the length of the water column gets longer and longer, the frequency starts to go down because of that inverse relationship.